My name is Andrew Davis. I'm going to talk you through my project implementation. I start with importing all the libraries I need and importing the dataset itself. After doing this, I inspect the data using data.info, data.describe, and data is null. Data.info and describe just sort of gives a better feel for the structure. It confirms that we've got over 40,000 entries. There's no missing values, so we don't need to sort of clean the data. Data.describe gives us a feel for the numeric data, gives us the mean, the standard deviation, minimum, and the maximum. The next thing I do is plot the histograms and the bar charts. This helps me sort of better understand what the data looks like to make sure that the data isn't skewed and that it's nicely balanced. We can see age distribution, for example. There's no sort of outliers in one particular age group. It's all sort of fairly evenly spread across. Engagement, medium is slightly skewed, but not enough to sort of have an effect on the model itself. Same with gender, there's a slight difference between male and female, but again, not enough to have an impact on the model. So after analysing the data, the next step is to prepare the data for modelling. I believe the first thing I do is drop the player ID. So we confirm. Yeah, so we drop the player ID. This doesn't really sort of provide us with any information, and it could potentially sort of harm or give sort of nonsense noise to the data, to the model itself. So we decided to drop this. Then I split the data into features and labels. So X contains all the input data and Y is the target. And by target, what I mean is that's the engagement level we're trying to predict. So machine learning models, they don't work well with text. So the next thing I do is to convert any sort of text data into numerical values using one-hot encoding. This converts the data, so the text data, into 0 and 1. And by using drop first true, this particular line here helps avoid redundancy and sort of keeps the data set clean. The next thing I do is use label encoder to encode the engagement level itself. So label encoding turns high, medium, and low into numbers. So 0 representing high, low with 1, medium with 2. So most classifiers expect the target to be numeric, so this is an essential part of the script itself. So we don't use one-hot encoding for this because we don't want multiple columns. We want a single label because this is a classification problem. Next, we split the data into training and test sets using a 70 and 30 split. Stratifying the data is really important. So by stratifying the data, we split it so that all engagement levels stay in the same proportion in both sets. So this prevents the model from being trained on sort of an imbalanced target. This next part again is really important. So using the standard scaler. So SVM support vector machines, they rely heavily on sort of distance calculations. If one feature is in a minutes, for example, in this data set, and another one is levels, the SVM would be sort of distorted towards one of these data points just because of the distance calculation it does. We only do this for SVM because decision trees don't need standard scaling. Next, we begin training our first data model, so the decision tree. Unfortunately, it's quite predictable. The train accuracy comes out as 100%. This means that the model has perfectly learned the training data. So obviously it's a clear sign of overfitting. And then test accuracy drops around 84%, confirming this. This means that the model doesn't generalize to sort of test data. Decision trees, they tend to overfit, so this isn't a particularly surprising turn of events. As long as we tune the model later on, which we do, it does solve this problem. The next step we take is to implement the linear SVM. The accuracy between both the test and the trained data is very, very close. This shows that it generalizes better than the decision tree, which is to be expected. But the linear boundary may be too simple for this data set. Before moving on to implementing the RVB kernel, I checked what the ROC AUC score was for the decision tree and the SVM linear model. So this basically measures how well the model separates the class overall using predicted probabilities. So you're looking for a sort of a score as close to 1 as possible. Here we can see the SVM performed better than the baseline decision tree. So then we move on to sort of the more flexible SVM model, so the RBF kernel. This allows for a curved line, so essentially adds another dimension to the model. This allows it to capture sort of more complex relationships in the behavioral data. After running this, I print out the classification report. You can see a general improvement compared to the linear model. We can see that medium engagement class has the highest recall. This means that the model is good at spotting players in this particular engagement group. So next, having implemented the sort of the baseline models, we move on to the hyperparameter tuning using Grid Search CV. So Grid Search CV is a tool that sort of automates all the model tuning for us. So in this case, I give it a model, so decision tree, and a list of parameters. So it's max depth, minimum sample leaf, minimum split. It then sort of tries to use every combination and sort of cross-validates this and then picks out the best combination to give the best score. So after defining the parameters, I then fit the grid search down here. And then this gives us the best parameters for that particular decision tree. We don't want the tree sort of to go too deep, so these parameters will give us the best chance of not doing that and sort of reduce this overfitting. After doing that, then we evaluate the tuned tree and then print out the classification report here. So very nearly has a test accuracy of 90% again, so that's a big improvement on the baseline tree. Next, we follow the same process with a SVM model using the RBF kernel. So this attribute here, C, so it controls how strict the model is with misclassification, and then gamma then controls how far the influence of the single point reaches. The grid search then will use sort of all combinations of C and gamma to find the best overall combination, which is C being set at 10 and gamma at 0.01. Then we follow the same process to evaluate the tuned SVM model. You can see it reaches about 89% accuracy. The ROC and AUC scores are then calculated for both decision tree and SVM. SVM marginally better than the decision tree. So after this, then I built sort of a very basic table just to give us a summary of the scores of each model. So the tuned decision tree just about wins the accuracy test with pretty much 90%. It also has the best F1 score at 90%. The next part then is to sort of just visualize this a bit more. So I created this confusion matrix. From here, we can see that both models, so decision tree and the SVM, the medium engagement level, they both do very well on. And most of the mistakes are between sort of high and medium or low and medium, which makes sense because those are close in behaviour. So after these supervised learning models, we then move on to the unsupervised using k-means clustering. So my first attempt at this, I tried clustering on all features. So like we did with supervised models, we dropped the engagement level because that's our target. Follow the same process as before, as in standard scalar. Then we try and find the best cluster to use. So we use the elbow method and the silhouette score to try and determine this. These are then plotted below. As you can see, we can't really tell here what the best number of clusters it is to use. We should be using. The silhouette score tells it should be 4, but again, this is very, very low. It's not a particularly convincing score, but we decided to go with 4. Yeah, so the initial sort of clustering didn't give us much information. Obviously, I think there's probably too much noise around. Too much noise around the data. So there's no sort of real pattern it could pick up. So before moving on to try and potentially how to implement another unsupervised model, I decided then to just focus on behavioral features, so playtime hour sessions per week, average session durations. Again, I checked to see what the correct number of clusters were. Again, it doesn't really show a clear indication here, so again, I went for 4. Probably should have gone for, well, 6 is the highest, but there's not much difference between the two, and you do want to use 6 clusters for this, so I set it with 4. And from here, there was sort of a clear pattern. So here we can see sort of a summary of the clusters. Each cluster is around sort of 25% split between them. So we didn't have any sort of a tiny or huge group. And then I looked to see how engagement is split between each cluster. So the most interesting finding I came across was the sort of, in this way, it's representing this little table here. So these 4 represent each cluster, and you can see cluster 1 is completely dominated by highly engaged players. So, well, almost 84% is group are in high engagement category, which gives a strong sort of behavioural pattern for this sort of particular clustering. Just to go back to early in the script, cluster 1 was represented by very frequent sessions with long sort of play times. And then I look at sort of demographic data, but sort of no real patterns came from these. Again, they were fairly balanced across the whole data set. No sort of particular features standing out. Yeah, so the main sort of thing to take away from this project is that behaviour tells us far more about player engagement than demographics. And then this is sort of represented in my report, where I give further sort of guidance to the company about how they sort of should exploit this and potentially monetize this.